Metallurgy is the branch of material science and engineering that deals with the study of metals and their properties, production, purification, and usage. It involves the extraction, refining, and processing of metals to create alloys and other materials with specific mechanical, physical, and chemical properties. Metallurgical processes can be classified into four main categories: mineral processing, pyrometallurgy, hydrometallurgy, and electrometallurgy. Mineral processing involves the physical separation and concentration of minerals from ores. Pyrometallurgy involves the use of heat and chemical reactions to extract metals from ores. Hydrometallurgy involves the use of chemical solutions to extract metals from ores. Electrometallurgy involves the use of electrolysis to extract metals from their ores or to purify them from impurities. Each metal has its own unique metallurgical process based on its physical and chemical properties. The metallurgical process starts with the mining and extraction of the ore from the earth, followed by the concentration of the ore to remove impurities. The extracted metal is then purified through various techniques such as smelting, refining, and alloying to create the desired properties. For example, in the metallurgy of steel, the iron ore is first extracted and then concentrated through beneficiation techniques. The concentrated iron ore is then smelted in a blast furnace along with coke and limestone to produce pig iron. The pig iron is then refined by the basic oxygen process or the electric arc furnace process to remove impurities such as carbon, sulfur, and phosphorus. Alloying elements such as manganese, nickel, chromium, and vanadium are added to the refined iron to create different types of steel with specific mechanical and chemical properties. In summary, metallurgy plays a crucial role in the production of metals and alloys that are essential to our daily lives. The metallurgical processes involved in the production of each metal and alloy are complex and require a thorough understanding of the properties and behavior of the materials involved. Copper. Copper is a reddish-brown, ductile metal that has excellent thermal and electrical conductivity. It is commonly used in the electrical industry for making wires, electrical components, and electric motors. The metallurgy of copper involves the following steps. Mining. Copper is usually mined from copper-rich ores, such as chalcopyrite, bornite, and malachite. Concentration. The ore is then concentrated by froth flotation or by leaching with sulfuric acid. Smelting. The concentrated ore is smelted in a furnace to produce copper matte, which is a mixture of copper, iron, and sulfur. Conversion. The copper matte is then converted into blister copper by blowing air through it to remove the sulfur and iron. Refining. The blister copper is then refined by electrolysis to produce pure copper aluminum. Aluminum is a lightweight, silvery white, ductile metal that is resistant to corrosion. It is commonly used in the aerospace industry for making aircraft parts and in the construction industry for making doors, windows, and frames. The metallurgy of aluminum involves the following steps. Mining. Aluminum is usually mined from bauxite, which is a mixture of aluminum oxide and other compounds. Refining. The bauxite is refined by the Baer process, which involves dissolving the aluminum oxide in caustic soda and then precipitating it as aluminum hydroxide. Smelting. The aluminum hydroxide is then smelted in a furnace to produce aluminum metal. Casting. The molten aluminum is then cast into ingots, which can be further processed into various shapes and forms. Iron and steel. Iron is a grayish-white, ductile metal that is the most widely used metal in the world. It is commonly used in the construction industry for making buildings, bridges, and roads. Steel is an alloy of iron that contains small amounts of carbon and other elements, which give it additional strength and toughness. Steel is used in a wide range of applications, including automobiles, appliances, and machinery. The metallurgy of iron and steel involves the following steps. Mining. Iron ore is usually mined from hematite or magnetite ores. Concentration. The ore is then concentrated by magnetic separation or by froth flotation. Smelting. The concentrated ore is smelted in a blast furnace to produce pig iron, which is a mixture of iron, carbon, and other impurities. Refining. The pig iron is then refined by removing the impurities through the basic oxygen process or the electric arc furnace process. Alloying. To make steel, the refined iron is then alloyed with carbon and other elements, such as manganese, chromium, and nickel, to improve its properties. Forming. The steel is then formed into various shapes and forms, such as sheets, plates, bars, and tubes. Nickel. Nickel is a silvery white, ductile metal that is commonly used in the aerospace, electrical, and chemical industries. The metallurgy of nickel involves the following steps. Mining. Nickel is usually mined from sulfide ores, such as pentlandite, and laterite ores, such as limonite and saprolite. Concentration. The ore is then concentrated by froth flotation or by leaching with sulfuric acid. Smelting. The concentrated ore is smelted in a furnace to produce nickel matte, which is a mixture of nickel, copper, iron, and sulfur. Refining. The nickel matte is then refined by various processes, such as the Mond process or the carbonyl process, to produce pure nickel. Chromium. Chromium is a hard, lustrous, silver-gray metal that is commonly used in the production of stainless steel and other alloys. The metallurgy of chromium involves the following steps. Mining. Chromium is usually mined from chromite, which is a mineral that contains chromium oxide. Concentration. The ore is then concentrated by gravity separation or by magnetic separation. Roasting. The concentrated ore is then roasted with soda ash and lime to convert the chromium oxide to sodium chromate. Electrolysis. The sodium chromate is then electrolyzed to produce chromium metal. Common uses of these metals are copper, electrical wiring, plumbing, roofing, coins, and electronics. Aluminum, aerospace, construction, transportation, and packaging. Iron and steel, construction, transportation, machinery, and appliances. Nickel, stainless steel, alloys, batteries, and coins. Chromium, stainless steel, plating, and alloys. Overall, the metallurgy of these metals plays a crucial role in producing materials that are used in a wide range of applications, from everyday household items to high-tech industrial equipment.
Metallurgical operations are a set of processes that are used in the extraction and refining of metals. These operations involve different physical and chemical methods that are used to separate metals from their ores and purify them. Here are some of the most important metallurgical operations and their applications. Ore preparation. This operation involves crushing, grinding and sorting of ores to prepare them for further processing. Ore preparation is essential in maximizing the extraction of valuable metals from ores. Roasting. Roasting is a process of heating ores in the presence of air or oxygen to remove impurities and convert them into oxides. Roasting is used for the extraction of metals such as copper, lead, and zinc. Smelting. Smelting is a high-temperature process used to extract metals from their ores by melting them along with a reducing agent. Smelting is used for the extraction of metals such as iron, copper, and lead. Refining. Refining is a process of purifying metals obtained through smelting or other processes. This operation involves different methods such as electrolysis, precipitation, distillation, and solvent extraction. Refining is used to produce high-purity metals for various applications such as electronics, aerospace, and medical devices. Alloying. Alloying is the process of mixing two or more metals to form an alloy. This operation is used to improve the mechanical, chemical, and physical properties of metals. Examples of alloys include stainless steel, brass, and bronze. Powder metallurgy. Powder metallurgy is a process of making metal powders and using them to produce products by compacting, sintering, and shaping. Powder metallurgy is used to produce various products such as gears, bearings, and cutting tools. Casting. Casting is a process of shaping molten metals into desired shapes by pouring them into molds. Casting is used to produce various products such as engine blocks, turbine blades, and structural components. Welding. Welding is a process of joining two or more metals by heating them to their melting points and fusing them together. Welding is used to produce various products such as pipelines, bridges, and automobiles. In conclusion, metallurgical operations are essential in the extraction, refining, and processing of metals. These operations have various applications in different industries such as mining, aerospace, automotive, and electronics.
Petroleum is a naturally occurring liquid mixture of hydrocarbons that is found beneath the Earth's surface. It is formed from the remains of dead organisms that were buried and subjected to heat and pressure over millions of years. Fractional distillation is a process used to separate the different components of crude oil based on their boiling points. The process involves heating crude oil in a distillation column and then condensing the vapors at different temperatures to separate the different components. The process of fractional distillation of petroleum can be broken down into the following steps. Heating. Crude oil is heated in a furnace to around 400 to 500 degrees Celsius before being fed into a distillation column. Separation. As the heated crude oil rises through the distillation column, it begins to cool and condense at different heights based on their boiling points. The components with higher boiling points condense at the lower levels of the column, while the lighter components with lower boiling points condense at higher levels. Collection. The condensed components are collected at different levels of the column and are referred to as fractions. The fractions are collected and stored in different tanks for further processing. Processing. The fractions obtained from fractional distillation are further processed to obtain various petroleum products such as gasoline, diesel fuel, jet fuel, lubricants, and asphalt. The different fractions obtained from fractional distillation of petroleum include gasoline. This fraction has the lowest boiling point and is collected at the top of the distillation column. Gasoline is used as a fuel for automobiles and small engines. Naphtha. This fraction has a slightly higher boiling point than gasoline and is used as a feedstock in the petrochemical industry to produce chemicals such as plastics and solvents. Kerosene. This fraction has a higher boiling point than naphtha and is used as a fuel for jet engines and heating. Diesel. This fraction has a higher boiling point than kerosene and is used as a fuel for diesel engines and heating. Heavy fuel oil. This fraction has a higher boiling point than diesel and is used as a fuel for large marine engines and power plants. Lubricating oil. This fraction has a higher boiling point than heavy fuel oil and is used to produce lubricants and greases. Asphalt. This fraction has the highest boiling point and is used to produce asphalt for road construction and roofing materials.